So thank you very much for the invitation. So my talk would be devoted to some to the following topic. So Adrien will be locally compact group. I will be interested in the Chabauty space of G. So, denoted by that G is space of subgroups, which is naturally endowed with a topology, which is called the Chabauty topology. And on the action of G on its Chabauty space by conjugation. So let me record what the definition of the Chabauty topology. So a basis of open set for this topology is given by sets of the form. So you can choose your favorite open sets, finite number of G, and your favorite compact set of G. And then you declare the basis of open sets is indexed by this data. And to put a topology on the set of subgroups, you just declare the set of subgroups of G that intersect non-trivially the VI and that is for every I. And that intersect trivially K to be open. Okay. So why to do this? So just I guess you all know very well this topology, but just to clarify the thing, if G is countable, it turns out that there is a much quicker way to define this topology. You can just see the set of subgroups as a subset of the set of all closed subset of G. Naturally, there is a product topology, and it's closed inside this. But I will talk also about locally compact groups. So why to define this topology? Because there are many reasons. One reason is that it is a very useful tool when one studies actions of groups on measure spaces or on compact spaces, maybe. Because this topology appears naturally in the study of the stabilisers. So the purpose of my talk will be to describe several examples of groups for which you can understand pretty well the dynamics of the action on its Chabauty space. And out of this, you can show that these groups exhibit some sort of lack of non-free actions. So by the way, that will be based essentially on joint works with Adrien and Boudec. So joint work of ours from last year and some ongoing work here at the Institute, which is still in progress. And I also mentioned a little more quickly as well to Tsankov. So in the first part of the talk, I will take a purely topological dynamical point of view. And the main object of study will be the following, what is called uniformly recurrent subgroups. Study, of course, the notion is natural, but the study was suggested by Glasen and Weiss. So, what is a uniformly recurrent subgroup? supposed minimal subset of the Chabauty space, invariant. Okay. So what are basic examples of such things?
So it's not actually a subgroup.
It's not a subgroup.
This last time.
I did not choose the terminology. It is not a subgroup, but it is useful to go this way because sometimes you confuse. So, by the way, this is gonna be abbreviated QRS. So sometimes it is useful to confuse this set with a typical element of it, which is actually a subgroup. So and I will freely confuse the two notions. It's usually not a problem. Okay, it's always clear from the context that we're talking about the subset of the subgroup. So the first obvious example is just a normal subgroup. It's nothing but a fixed points. The second obvious example is so for instance a co-compact subgroup. So the conjugacy class third, and more general example, so URSs, as I said at the beginning, appear naturally when you study actions of groups on compact spaces in the following way. So suppose G is acting on a compact space minimally. It turns out that you can cook out of this a URS in the following way. Right, so the first idea, of course, would be to look just at the collection of stabilizers. But this is not quite a URS because in general it's not even a closed subset. It's here an invariant subset, but it's not closed. So what you do is you close this. But now you may lose minimality, so it may not be minimal. But what is true is that this set contains a unique minimal subset. Sorry. This called stabilizer URS of this action, and denoted as GRS. So, if you're familiar with sorry. Okay. So, okay. I guess I have to hide something. So if you've already seen talks, so this notion is clearly inspired. I didn't talk about it, but maybe I will at the end of the talk. But it's clearly inspired by the notion, which is very well studied nowadays, of invariant random sample, which is just an invariant probability measure on the Chabauty space. And every time you see a talk on these objects, you also see something like this. So the main examples are normal subgroups, and then you can hook out one out of each measure preserved reaction on a compact space. And then the first basic result you see is that conversely, every IRS is of this form. So you can, and for IRSs, so already this construction is slightly more delicate. And whether every URS of this is of this form was a question of Gran's bias that was open until recently. And the answer is eventually not so complicated. And one reason to be solved by the section to the Tsankov. And independently by Gaborelli for finitely generated groups. So conversely, so for every G locally compact, and for every HRS G, there exists a minimal action on some compact space such that not only you have this, but even you don't have this problem. Such that if you wish, H is exactly equal to the collection of point stabilizers. Okay. So, just to conclude this introduction to these objects, let me also mention another result which is of completely different nature, but it gives some motivation to study this. But I will not talk about it. So this is a very nice direction, but it's easier to present our Kennedy and Kennedy combination of the results. So assume G is countable. Then the following are equivalent. And I will not define the terms appearing here because, as I said, I will not talk about it. So I just want to know that this connection exists. So the first condition is that G is sister simple. Second is that G has freely and it's the universal December boundary. And the third condition is in terms of your S's, G has no non-trivial URS consisting of minimal sum. Okay.
So what's the example where this is not closed? This is GX.
Almost any. Like, so, for instance,
There you construct it.
what do you mean? Well, this is not closed?
Yeah.
Yeah, so if G is countable, for instance, the Chabauty space is totally disconnected. If you take X to be an unconnected space, it will never be closed. It being closed is equivalent to the stabilizer map being continuous, and this can happen only if the space is itself totally
Is it
disconnected.
equivalent?
I think it's equivalent. Okay, maybe I'm not totally sure. I think it's and actually, in that statement, you also have that it is continuous. So the actual statement. So why I mentioned this theorem? Because this was a big motivation for what I'm gonna talk now. However, I don't wanna take this angle. So now I'm gonna talk about the joint work with Adrien and Boudec, which was originally motivated. Our original motivation was to study the sister simplicity of subgroups. However, it turns out that I decided in this talk to take a different angle. So of course this is all very nice. So in principle, these three statements tell you that if in principle you are able, even a group, to understand very well the Chabauty space, its topological dynamics, the topological dynamics of its action on the Chabauty space, in particular to describe the minimal invariant subset, then you can get a lot of information. For instance, you can get information on how it can act minimally on compact spaces in general, and you can get information about sister simplicity and its Fürstenberg boundary that is usually a mysterious space. However, for most groups you may be used to, this is not very reasonable, because very often there are too many such sets and you cannot describe them. So first of all, I would like to give you an example in which this can be done, and it can be used to prove a nice result in the setting of minimal actions, compact spaces. And these are Thompson groups. Consider the Thompson groups. So these are three groups, usually denoted F, C, and B. F is a group of homomorphisms of the interval. E is a group of homomorphisms of the circle. And E is a group of homomorphisms of the Cantor set, and they share the same definition in this space in which they act are different. They are the groups consisting of homomorphisms which are locally of the form x max to 2 to the n x plus 2 to the plus say q, where n is an integer, q is a dyadic fraction. And by locally I mean except perhaps for T and B. For T and F, sorry, for B there is no problem. At the neighborhood, finitely many points. Which are dyadic. Okay, just precise. So this is what it means for F and T, and for B it just means there isn't, so that you interpret this as binary coding of natural number. So so this is there is a difference between these three groups, especially between the first one and the second two ones. Just in terms of how they are defined. So they're groups defined by an action on a compact space, which is the setting I want to be in. But the big difference is that these actions are minimal. Well, this is not. And And these actions give rise to nice URSs, so they are highly non-free by definition. This gives so in a highly non-free way, and it's interesting to ask whether they can act non-freely in some space in a substantially different way. And it turns out that this is not the case. So I will focus on T maybe just as an example. Let P act on a compact space minimal, minimal and not topologically free. I will say later what I mean by topologically. And then it turns out that this action is essentially closely related to the original action in the following way. And there is this continuous subjective map equivariant from this space, which a priori would be anything to the circle, equivariant. Of course, this is a rather weak condition a priori because you can ask, okay, what's happening in the fibers? However, you can also say something rather precise on what's happening in the fibers, so essentially nothing. Roll points in base. So you can look at the fiber. This can be complicated as a space. However, what is true is that the stabilizer of the point here will act on the fiber, and it will act trivially. But this is true for all points except perhaps counter domain.
What is topologically free?
I will explain everything now. So.
Okay.
What is topologically free? I'll explain right now. An action on a compact space is topologically free if the set of points with trivial stabilizer is a dense G delta. But if G is countable, so this is equivalent by, as you can say, check by the way. So this is equivalent to the triviality of the URS associated with this action. And if G is countable, this is the same as saying that for every given element of G, it sets of fixed points as empty interior. Okay. So let me make a couple of remarks on this. So first of all, note that the conclusion among non-topologically free actions is optimal because there are actions which are not conjugate to this one and are not topologically free. For instance, one way to build them is to blow up orbits on the circle. You take your favorite orbit, you replace every point by a couple of points, you get a Cantor set. And you can even do this for all orbits at once. You get a non-metrizable compact space on which you act, and then you can, of course, glue them back together. But so this is saying that if you want to have a non-free action of this group, this is essentially the only kind of operations you can do. So you can blow up and move around fibers rigidly. And also, you cannot expect such a conclusion to be true for all actions. So first of all, of course, not the second sentence, because this implies that the action is not free, but also because space of the free actions of a countable group is always very wide. For instance, every group acts freely on a compact space by even minimally by preserving a probability measure. And this implies that, of course, if you have a probability measure here, you push it, it's not invariant. Because the action of the circle is highly non-invariant. And so, what else can I say about this? So yeah, for instance, okay, such rigidity, there were some cases in which similar phenomenon was known for these groups. So, by the way, this is kind of a sample theorem. Now I will explain kind of the methods that give it, which are important things. But something that was known, for instance, is that if X is the circle, so T is a group of homomorphisms of the circle, then every minimal action on the circle is actually conjugate to the standard one. This you can prove, for instance, using bounded cohomology methods, which are not available here. And you can also recover it by combining this result with the work of Gis and Margulis about free presence or absence of free subgroups in groups homomorphism of the circle, because using that you can actually show that if T acts minimally in the circle, then the action cannot be topologically free, because T has huge subgroups that do not have free subgroups. And then you can check that this map combined with this description is forced to be actually conjugacy. But this is not quite this kind of an accidental consequence. So in particular, there is also some bad news about this kind of phenomenon. That is, so all these Thomson groups are very mysterious. In fact, the reason why they're very mysterious is that their Cayley graph, if you wish, is extremely complicated. You cannot picture it in any possible way. And the way they're usually studied is by exploiting the actions, the spaces, and the fact that these actions are highly non-free is key, because this allows to study orbits. The orbits have a very simple behavior. And so this theorem, a similar conclusion is true for, so exactly the same conclusion is true for V, and for F, what is true is that essentially that means no minimal action which are not free. So, that one fixes at the endpoints. In general, what is true is that there will be a minimal action will factor through the organization. So it says that essentially, if you want to say something that you're not able to say using this standard action that are given, but you're forced to look at free actions, and free actions are very complicated. So, I don't know. Let me just say a word about how this is proved. Of course, how to prove such a thing is 2 steps. So first one, which is the key point I want to talk about, is classify all your S's of T. And this turned out to be just very few, the ones you imagine. There are two obvious ones, and there are a third one that appears naturally from the action given by, and there is nothing else. And then once you have this, so then if I give you an action that is not topologically free, you know that its associated URS is the same as the one on the circle, and from this you can work a bit and construct. I will not talk about this part because it's less interesting, but I will just say a word. So this grew out actually from a more general study of URSs of groups given by an action by homomorphism on a space. So let me say an ingredient to prove this. So here's my set in the following setting. Assume G is a countable group. And assume that G is given by an action by homomorphism on a space that for now I just assume to be Hausdorff. And the action I want it to be faithful. And so I need some notation. So for U in Z an open set, I will denote G index U, the set of elements of G which are supported in U. So supported in the set theoretic sense. So this is the component. I will call this the rigid stabilizer. So just a quick comment on why to consider such a setting. So what I will say is actually true in general, but what I implicitly assume here is that the subgroups are very large, which is what's happening for Thompson groups, for instance. And why considering such a setting? Because of course, if you wanna have some hope to observe such a phenomenon, then you have to be in a so. Of course, a necessary condition is already that the group has very few normal subgroups, or is simple, for instance. So such a thing can only be true for a simple group. It's apparent from here. If the group admits actions of quotients, then you cannot, of course, relate them to and
I'm sorry, I missed the notion. It's a fix of G, is that it's the set of elements that fix points not in U. I just consider that.
is the set of is the set of G and G such that G is the identity restricted to the complement of U is the so supported in U, but I don't say supported because it's not the closure. It's and and groups of this kind, that given an action of homomorphism with rich rigid stabilizer, are a well-known source of, so at least, of simple groups. Okay. And why is this true? Because for such a group, you can play a lot of commutator games, and this will kill the presence of normal subgroups by making such rigid stabilizers appear. So such commutator games are not available if you're working with your S's and with normal subgroups. So what I'm gonna state now is a technical result that replaces Until when do I have time?
You still have 25 minutes.
25 minutes, okay. So let me state it as a long proposition. So let G act on Z as above. And let H be a subgroup. Then one of the following must hold. Either H is so a subgroup in particular an element of the Chabauty space. It could be that it is very small when seen in the Chabauty space, meaning that there exists a sequence that accumulates H on the length. Or, if this is not the case, what's going to happen is the following thing. There exists U, a non-empty open set, and so K a subgroup of H, gamma a finite index subgroup of the rigid stabilizer, so the set of elements supported in U. So what I want to say is that H is big when you look at its action on Z. And by this I mean that it witnesses a big part of these rigid stabilizers. Just like for normal subgroup you make rigid stabilizers appears with commutator rings. So, and big part means a finite index subgroup of some rigid stabilizer. Because K, so a subgroup of H, will have the following property. It preserves U. And once it preserves U, you can look at what it does when you restrict it to U. So and just look at elements inside U. And in restriction to U, what you see is gamma, which is already is in U. But you have no idea what's happening outside. So using element of H, you can mimic in U a lot of what G can do. But also with some noise outside that you don't control, and this is a nice tool. So actually, as a go back to the equivalence to the sister simplicity business, our motivation originally was exactly to have a nice criterion to show sister simplicity of groups that appear in this way. And this, for instance, rules immediately. So it's a sufficient condition that rules out the existence of amenable URS, which is just that all the subgroups like this are non-amenable, which is something that you can easily check. But this is not quite enough to prove such a thing, because it's too general in a sense. I just took an actual positive space, and so now if I take a URS of T, and I want to say that's related to the original one, with some assumptions, there is a stronger conclusion. So, moreover, assume that the space is compact, and let's make an assumption on the action of G on the space, that this action is extremely proximal. So extremely proximal means the following. For every closed set, Z proper, you can shrink it to a point. using a sequence of elements of G. Then you can replace two by the following condition, 2 prime, which is the same, so there is this U non-empty open set. And the beginning is the same. I finally make subgroup of stabilizer, but this time you will have a the commutator subgroup of gamma is contained in H. By contained, I mean really as group of monomers. So you also can do whatever you want in U in slightly smaller subgroup, but this now you don't have any noise outside under this stronger assumption, which is, for instance, verified there. And this, using this, you can, it's kind of an exercise to go from here to there. Take a URS, you have this information which is very strong for such kind of groups, and then you play a bit more and you understand everything. Okay. Now we'll switch to something else. I still have 20 minutes, I think. I will talk about some work in progress. Again with Adrien. That is still quite, it's very much in progress, but still I want to say we're working with this, which is about non-discrete locally compact groups. And more precisely, what we're wondering is about non-discrete locally compact groups that have no URSs at all, and also no IRSs. So for this, I just need to tell you a word about IRSs since I cited it before. So invariant random subgroup. Is an invariant probability measure on the Chabauty space. Okay, so what are the examples? Once again, one is direct mass on a normal subgroup. There is another source of examples that it's worth mentioning, which are lattices. So gamma is a lattice in G. Then you can consider there is a natural map from the homogeneous space of gamma into the set of subgroup, which to every coset you can associate its well-defined conjugate of gamma. And so since here by definition there is an invariant measure, you can push this here and get an invariant measure there supported on the conjugated class of gamma. So in this context, IRSs are a simultaneous generalization of normal subgroups and lattices. And a similar discussion to what I said before for IRS, for URS, so mixing letters applies. So the most general source of examples is when G acts by measure preserving transformations on some probability space. Then you can push through the stabilizer map the probability measure onto a set of subgroups, and you will get an IRS. And and this is the more general example. So every IRS is this. And what's we do in this process? So we focus on the following two questions. So, are there non-discrete locally compact groups with no IRSs at all? By no, I mean apart the obvious ones, which are the direct mass on G and on the trivial sub and the complex combinations. And the second question is it's obvious relatives. So for URS. So this question I think is due to get under, but I'm not sure, so I will not write it down because I'm being fit. So, some comment, why non-discrete? There are two reasons why. First of all, because it is especially interesting for non-discrete groups because of this. So, because for non-discrete groups, IRSs do not just generalize normal subgroups, but also lattices, which is something that discrete groups are not very interesting. And in fact, for a long time, it was not. This question kind of arises from work of Bader, Capras, Gerander, and Moses, who provided examples of simple locally compact groups that have no lattices. So, examples is the narrating group, the group of almost automorphisms of a tree. So that have no IRSs of the two basic kinds. This is a natural question whether you can find examples that have no IRSs at all. This is open for the narrating group that they consider. And the other reason why non-discrete is necessary in this question is that for discrete groups there are many answers. So I will many positive answers. So I will just mention some of these. So before I do this, I just want to say where I want to go. So what we managed to do so far is to find a cheap answer to these questions. But I will present at the end a group that answers affirmatively both questions, but with the serious drawback that it is not compactly generated. Now we're working to find some compactly generated examples. I'm pretty optimistic for the first one, not at all for the second one. Actually, I cannot even imagine a compactly generated local compact group which is not given by an action, so which is a candidate for this. But for the first, there are many candidates, even compactly generated, and there are, for some, it could be good. So, kind of to motivate the construction and talk about, let me just survey some for discrete groups. So there are two objects, URSs and IRSs. How many there are here? We write number. So, first of all, there is a very silly example on discrete groups, which also explains why the question is not so interesting, which has the Tarski masters. More generally, any simple group that have only countably many subgroups. It will not have URSs and it will not have IRSs, just for this reason that it does not have subgroups essentially. So the Zadarsky monsters are subgroups that have as few subgroups as they can have. But there are more interesting examples. So for instance, a very nice example that shows that there is no general link between these two objects is the finite alternating group. So this group, it's not difficult to see that it has no URSs. However, it has many IRSs. And in fact, you can classify them in groups. So Virtue classified them. And there are also examples that reverse this. So for instance, Thompson B, I talked about it also B before. So as I said before, these groups have only one non-trivial URS. But this URS does not carry a program invariant measure, and in fact they have no IRS. And you can also have examples which are more interesting than this and that have known of both. For instance, the right subgroup of Thompson group F. So why am I saying this? Because so going back to the question of finding non-discrete local compact groups that exhibit such a behavior, no, all actions are free in the appropriate sense. What is the way, a very much exploited way to obtain, let's say, exotic examples of non-discrete local compact groups? It is the following. So you start from a group that acts on some space naturally. For instance, Thompson group V acts on the counter set that you can see as the boundary of the rooted tree. And then you look for a compact group that also naturally acts on the space, so it lives in the same ambient group, the whole symmetric group of this space, and which is commensurated by the countable group you started with. If you have this, you can look at the group generated by these two guys, and it turns out that it carries a natural topology. Since the compact group inside is commensurated, you can declare it to be open, and this will define a unique group topology. For instance, for this example, there is a natural compact group which is commensurated by V, which is the group of automorphisms of the rooted tree, which V acts on the boundary. And this way you precisely discover the narrating group, which is the group I mentioned before, the four-order paper, but it has no lattices. So you can think maybe, okay, from the fact that V has no IRSs, and this group will be dense inside. So you can try to say, huh?
So can you recover V from the narrating group?
Well, it's dense inside. There is a dense copy of V inside. Then this was an observation of Cabras and the Metz, very beginning of the narrating group in this context. However, the fact that you have this group inside which is dense does not have static IRSs on the ambient group. And so it's still an open question. So now what I want to talk about is a cheat construction on doing this, but by giving up the requirement that the obtained group will be compactly generated, and which will allow to actually reduce the study to this dense group that you have inside. And the setting is as follows. So I will try to generalize examples that rather look like this or this. So assume gamma is a countable group. And I want it to be represented by a faithful action on some set omega. Because I will talk about supports of its elements and things like that. So, and assume you have a sequence di where each di is a finite subgroup of gamma. And these things satisfy the following. So first of all, you want the support of these finite subgroups to be disjoint. Secondly, this is what will force gamma to be non-finitely generated, and hence the group you obtain in the end to be non-compactly generated. You want that for every gamma in the group, the number of I such that the support of gamma intersect non-trivially the support of the I is finite. Yeah, so the picture is like this. You have gamma acting on a space, and you have a sequence of finite groups with disjoint supports like this. But elements of gamma only come until a finite match of pieces. So this is a very general, and in fact it's a very natural construction, and it has been used in already to produce examples of kind of exotic locally compact groups. So, in the following way. So I don't know. Now by given this slide with the notation, so I will note it like this: a sort of completion of gamma with respect to the sequence of subgroups. So this will just be the group generated by what? By gamma and a compact group. So when you have a disjoint sequence of finite groups like this, you also have the direct product, infinite direct product acting, which is a compact group. And so it's seen as an abstract group of permutations of omega, but with the topology, where this compact group is open. You declare it to be open. And you can do this, because it's very commensurate. And this construction is being used already many times, so let me give some examples. So first of all, a special case of this is it's called the semi-restricted product. And this also gives nice examples of groups. So it was used recently used by Cabras, Bader, Cabras, Gelander, and Moses again to give examples of metaphysical groups with non-uniform lattices, I think. And but this very special case is, so another example is due to Willis, Adrien, and Weiss, and also considered by Cabras and Cornelius. Which and is as follows: you take omega to be just the countable discrete set, and gamma to be the finitely supported permutation, and di to be the alternating group or some set segment. Infinity. And this already, so this is kind of it's used to disprove. For instance, Nicolas and Weiss use it to construct a group which has a dense conjugacy class and is locally compact. Cabras and Cormier use this construction to construct a group which is locally compact but does not embed into a compactly generated locally compact group. So that this is well known for this group is not told. So I would like to state, I don't dare stating a general fact about IRSs or URSs of this, but there will be some, but so let me just state the following proposition with these examples. So there are two nice examples. Assume as here, but you let some pi to be trivial. For instance, so you do the same I even and one. The conclusion is that then this group has no non-trivial URSs. However, it has many RSs. So now to conclude, I give an example where it has also no RSs, which is kind of relative to this. So yeah, now you have a lot of flexibility. You can choose your omega, you can choose your gamma, and there is no need to choose omega to be a discrete set. So choose omega, for instance, the two-adic dyadic rational numbers. Let gamma be a relative of Thomson groups B. So the following, a sort of compactly supported version of Thomson group B. So the set of homomorphisms and the dyadic line, which are compactly supported, and locally the form x gives to so it is dilated by a power of 2 and plus a rational number. And in this group there are many finite subgroups, so you have a lot of flexibility to find this construct to play this game. And so I don't want to state it exactly because I'm running out of time, but let me say under natural conditions, this sequence I, the group I has no IRSs and no. Okay, and the reason is that so in this case then this group has no nice discrete group and you can reduce. And I will stop here.
This last one is some kind of a Thomson group in
Yeah.
a different setting where but so this Q2 Q in the notation here. Q2 means what I think Q2 is
Yeah,
the two-adic numbers.
two-adic rational.
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 Yeah.
It's Q with a different valuation.
Yeah.
So
No. It's the completion of Q. That's it.
Oh, I see what you mean. It's the dyadic field.
Right. So it's just a complicated way to say, you know,
Right.
you can. So this set-wise is just n times the other group. Just right.
Yeah.
And so you do. So you know, it's kind of a locally compact counter set.
yes.
Where you. So in my mind, they call this group VLOC.
And
Because
the
it's kind of
homomorphism, they jump from one layer to another.
yeah, they're allowed to mix layers as well. They need not preserve them, but they're just compactly supported, and you know, you fix some compact set and you do B inside and outside.
Yeah, so it's a variant on Thomson's group V.
Yeah, exactly. It's probably isomorphic to the neighbor stabilizer of 2 points in the counter set for the standard So I mean, you fix 2 points and you look at all elements that fix a neighborhood of these points. And it must be something like that. Check if it's really the same.
And the reason it has no URS is a bit like the classification of URA.
Yeah. So sorry, I forgot to say a very important thing. To prove this, we use key. It's a key tag. So here we use the result of Boudec manuals for IRSs, and we use our previous results that I mentioned before for IRSs.
So, can you say quickly in what way your previous result shows the terminal?
Yeah, so actually it's even easier here. For instance, the thing so this action is extremely proximal, and yeah, if you can co-participate to a point, it doesn't matter. So the statement I said before, the second part, does not need the action to be minimal. So if the action is extremely proximal, you contain the right subgroup of a finite index subgroup of some rigid stabilizer, which in this case is usually the rigid stabilizer because they're simple groups, and then you can dilatate this and get to the whole group.
And it's indeed the resulting group is not discrete.
No, this is not a discrete group. But of course, as I said, it's not compactly generated, and there are there are other candidates for compactly generated examples, but this will never get to compactly generated because by construction it cannot be such.
That's all.